Hello students and welcome to another video. I'm your teacher, Mr. Flynn, and today we're going to be talking about rates of reaction. Okay. Now, as we go through this is a pretty small section. Reaction rates are something that goes in a lot more detail, but we're only giving it a day in class to go through these. We're going to do a lab with this. But basically, I just want to review some kind of major concepts and let you guys go in the lab and work on some experiments. All right, so basically a reaction rate is a ratio between two related quantities expressed in a different unit. Okay, it's like saying you're driving down the road at 10 miles per hour. Okay, so what we're saying is distance versus time. That's what a ratio is, or in other words, a rate. All right, a rate is like your rate of speed is 10 miles per hour. You're comparing distance for time. Okay, you're relating two different things together. And in this example, what we're doing is measuring the rate at which our reactants are used up to form products. Okay, an example of this, okay, could be like rusting. Rusting takes a very long time for it to occur. Okay, but we can certainly speed up the rusting process. There's ways that we can manipulate the rate at which that reaction occurs. Okay, but that's basically the idea here, is we can control how fast a reaction occurs. Okay, and the idea here is we have this idea called collision theory. Okay, and what we're doing is we're trying to make atoms as effective as possible at reacting with each other. Now, what we're doing is we have to make sure that atoms and molecules are oriented correctly when they run into each other, right? So for example, if you have a water molecule and it hits a certain way, it won't break apart. But if you hit it on a certain other side, it will break apart. And so we want to form as many collisions as possible and to have them be successful. All right, we want our atoms to hit just right as they bump into each other to break them apart. All right, and you need a sufficient amount of kinetic energy. Kinetic energy is the energy that's related to motion. So these atoms, if you think about it, if they're all moving around really fast, they're all going to be bumping into each other, and they're going to react much quicker. That's why when we say if it's in a gas phase, it reacts much faster than when it's in a solid phase, because the atoms in a gas phase are moving really fast. They're moving around with each other. Okay, like if you remember from earlier in the year, we put oxygen gas and hydrogen gas together, and we lit it on fire, and it went boom, right? And it happened very quickly because they're both gases, and when we started that reaction, it released a lot of energy, causing the atoms to move even faster, and then now all of them are hitting and bouncing off each other and forming water, and it happens very quickly. While on the other hand, rust is a solid, and it's interacting with a gas on the surface, and it's just slowly happening. Okay. Now, there is ways in which we can change the rate of reaction, and that is increasing the temperature, decreasing the particle size, making it smaller, and then increasing the concentration. All right, so if you increase the concentration, there's going to be more opportunity for more atoms to interact with each other. So it's all about interacting. It's all about mingling. It's all about getting things to interact with each other. Okay. Now, there is other ways to do this. All right, and that is by using a catalyst. Okay. A catalyst is something that uses. Actually, I'll back up. Let's talk about what activation energy is first. So activation energy is the energy required to get a reaction started. So if you remember from my balloon example, I have hydrogen gas and oxygen gas together in the balloon, and I needed to give it a little bit of a bump to get started, and that bump is heat. So I put a flame next to the balloon, and as soon as it melted that kind of polymer plastic on the outside of the balloon, that exposed the hydrogen and oxygen to a heat source, and that activated the reaction and got it going. All right, it's the energy required. Okay, it's a barrier of sorts. Okay, you have to overcome this barrier to get those atoms moving just fast enough to hit each other, to break apart, to form new products like water. And when that one or two water molecules are formed, it releases enough energy to keep the reaction going, and it propagates through the entire balloon. Okay, and what a catalyst does is it lowers the activation energy. Okay, another example of this was elephant toothpaste. When we did the elephant toothpaste demo, and if we haven't done it, we'll do it together in class. Just remind me. All right, we'll do this. What happens is we have hydrogen peroxide, and it's just decomposing really slowly. Okay, it's decomposing slowly, and we want to speed up that decomposition process. And so when you put in potassium iodide into the solution, what it does is it breaks down the hydrogen peroxide really quickly, releasing a lot of oxygen gas, and it forms those bubbles when you put soap and food coloring in it. It basically, as the gas is created, it generates all those bubbles because the soap is creating the bubbles that's being formed, all right, all that gas that's being let off, and we're capturing it, okay, in those suds. All right, so a catalyst is about lowering the activation energy. It's making it easier, in this example, to decompose rather than letting it sit and decompose in the course of months. We just rapidly did it with potassium iodide. And now, the thing about potassium iodide is it's not consumed in the reaction, so it's actually not even part of the reaction. When we write it, right, this example, we have H2O2. Hydrogen peroxide is going to decompose into water and oxygen. So where's the potassium iodide? Where do we write it? Well, we write it right above the arrow, because it's part of the reaction, but it doesn't get consumed. It's not being broken down. It's not being used or turned into something new. It's just there, and it's causing it to speed up. Okay? And the reason for this is actually pretty complex, and there's a lot of scientists trying to figure out why exactly is potassium iodide and these other certain compounds like platinum, why are they such good catalysts? And the main idea is that they help orient atoms a certain direction, so when they bump into each other, they break. Okay, they're easier to break apart, and that's basically what collision theory is all about: is creating more opportunities for atoms to bounce and interact with each other. Okay, all right, that's about it for reaction rates as far as my class is going. But if you go into college, there is going to be much more to this. We do a lot more problems in math, etc. But we're just trying to hit the big overarching ideas. Okay, thanks again for watching. Till next time.